Let's get right into it. In this explainer, we are going to build your calculus intuition entirely from scratch. I'm talking absolute ground floor. If you've ever felt completely overwhelmed by all those symbols and limit equations, seriously, don't worry. We're going to start off by looking at the world like a 4-year-old might, and by the end, you'll be confidently differentiating complex polynomials and mapping out their exact shapes with rigorous mathematical proofs.
Here's how we'll build this floor by floor. We'll cover the basics of change, then polynomials and fruit baskets, followed by proving the power rule, reading the signs, and we'll wrap up with a summary and some practice.
Starting with section 1, the basics of change.
Imagine a little toy car just zipping across the floor. If I ask you, how quickly is its distance changing as time ticks by? Well, you wouldn't need a math degree to answer that, right? You'd just say that's its speed, and you'd be spot on.
So the crucial takeaway here is that a derivative is literally just a formalized mathematical word for measuring that speed. Before we dive into all the heavy algebra, just anchor yourself to this single idea. The derivative simply tells us how fast our y value is changing whenever we tweak our x value. Let's visualize this with a super simple analogy. Think of a kid walking. When y goes up as x moves forward, their elevation is increasing. They're walking uphill. That is a positive derivative. But if they're walking downhill, their elevation is decreasing. That's a negative derivative. And what if they're walking on a completely flat, perfectly level road? Well, their elevation isn't changing at all, so the derivative there is exactly 0. Moving right along to section 2, polynomials and fruit baskets. Now, the word polynomial might sound kind of intimidating, but it is really just a math expression made up of individual pieces. We call these individual pieces terms. So, for example, if we have the equation y equals 6x cubed plus 4x squared minus 2x plus 7, well, those 4 distinct chunks, those are our terms. What's really fascinating here is how we can tackle these terms one by one, using something called the sum rule. Think of a polynomial like a big basket full of apples, oranges, and bananas. If you want to figure out how the total amount of fruit in that basket is changing, you can just count the change in apples, add the change in oranges, and add the change in bananas. Mathematically, it's the exact same. The derivative of the whole polynomial is just the sum of the derivatives of its individual terms. We can differentiate every single piece entirely separately. All right, part 3, proving the power rule. Time to derive the shortcut. To differentiate a term that looks like a variable raised to a power, we use the famous power rule. It's basically a simple 2-step dance. Step 1, you bring the exponent n down to the front to multiply. Step 2, you just reduce that original exponent by 1. So, a times x to the power of n magically transforms into a times n times x to the power of n minus 1. Make sense? If you have 5x to the power of 3, the 3 comes down and multiplied by the 5 to make it 15, and the exponent drops to 2. So you get 15x squared. But wait, as I promised, we're going all the way to rigorous mathematics. We aren't just memorizing some magic trick today. This rule comes directly from the foundational limit definition of the derivative. To find the rate of change, we take x and give it a tiny, microscopic nudge forward, which we'll call h. We look at our new y value, we subtract the old y value, and we divide by that tiny change, h. We write this out as the limit as h shrinks to 0 of f of x plus h minus f of x, all divided by h. Let's actually see how this builds. If we take our new term, a times x plus h all to the power of n, we have to use binomial expansion. That expansion gives us x to the power of n plus n times x to the power of n minus 1 times h, plus a whole bunch of other terms that all have h squared or even higher powers of h. Now, when we subtract our original term and divide everything by h, that vital first h just cancels right out. And as h approaches 0, every single remaining term that still has an h attached to it completely vanishes into nothing. The only surviving term in that entire massive equation is a times n times x to the power of n minus 1. And boom, we have perfectly proved our power rule from first principles. By applying that exact same logic, we get 2 extremely handy shortcuts. For a linear term, something like a times x, the derivative is literally just a. Why? Because the slope of a straight line is constant. If y equals 7x, the derivative is just 7. Every single time x moves by 1, y moves by 7. And for a constant number, let's call it c, the derivative is exactly 0. Remember our toddler walking?
A flat road has absolutely zero change. No matter where you are on the x-axis, y just isn't going up or down.
This brings us to section 4, reading the signs. Let's map out some shapes.
We have a very systematic 3-step recipe for creating what we call a sign chart. First, we differentiate our polynomial. Second, we factor that derivative to find the important numbers. These are the exact spots where the derivative equals 0, meaning the graph is perfectly flat. Finally, these 0 points divide our whole number line up into different regions. We just test random numbers inside those regions to see if the overall derivative is positive or negative. Let's map out a factored derivative together. X plus 3 times x minus 1 times x minus 6. By finding our zeros at -3, +1, and +6, we chop the entire number line into 4 distinct regions. When we pick a test number in that first region, all 3 factors happen to be negative, and a negative times a negative times a negative gives a negative result. That means our function is walking downhill there. As we move across the intervals, you'll see the signs alternate, showing us perfectly alternating between decreasing downhill and increasing uphill movement.
So let's apply this exact recipe to a real polynomial you might actually see in your textbook. Y equals x cubed minus 3x squared minus 9x plus 27. First, we differentiate it using our power rule. Then we factor it, discovering its critical 0 points are at -1 and +3. This gives us 3 regions to test. We drop a test number into each, and we see our function goes from increasing to decreasing and then right back to increasing.
And this brilliantly illustrates a profound mathematical truth. Right where the derivative is exactly 0, the behavior of the line changes. When we switch from increasing to decreasing, we have found a local maximum. That's the very peak of the hill. But when we switch from decreasing to increasing, we have found a local minimum, the absolute bottom of the valley.
Finally, part 5, summary and practice. Time to put it all together.
You are now fully equipped with a complete polynomial differentiation machine. You have the sum rule to treat terms like a fruit basket. You have the power rule, derived straight from first principles, to bring the exponent down and reduce it. You know that linear terms become constants, and constants vanish to absolutely 0. And finally, you know exactly how to build a sign chart to find the direction your polynomial is heading. You can confidently bypass those long limit calculations every single time. I want to leave you with a final challenge to test out your new calculus superpowers. Can you turn the crank on this machine for this new polynomial? Differentiate it term by term and figure out where this curve completely flattens out. Grab some scratch paper and give it a shot. And as you do, ask yourself this. If the first derivative tells us the slope, what secrets might a second derivative reveal about the shape of our universe? Think about it. I'll see you in the next explainer.